A Boolean AND query should not compare every posting. Skip pointers jump past impossible matches, cutting intersection work while returning exactly the same documents. You'll build square root spaced skip pointers and run a Boolean AND intersection that preserves exact matches while reporting saved cursor checks. I'm Professor Pi, teaching search and IR with simple Python. Start with a practical pain point. You have two sorted postings lists for two search terms, and you need documents that contain both. With small lists, this is trivial, but on large indexes, every unnecessary comparison costs time and CPU. Success here means returning exactly the same document IDs while doing fewer cursor checks. That gives lower latency and cheaper queries at scale, which is why systems add simple structural tricks before complex ranking. The intuitive idea is straightforward. Imagine two people reading two lists of numbers aloud and trying to find matches. If one reader can jump ahead when she knows the other reader's current number is still larger, she saves time. Skip pointers are those safe, pre-computed jumps. A small example will show the safety rule and the bookkeeping, so you can see exactly why results never change when skips are used. We will build a tiny inverted index with two terms, attach square root space skips to one or both lists, and then compare three approaches. First, we confirm the correct answer. Then, we simulate the naive scan and tout comparisons. Then we build and inspect skip maps. After that, we test a single guarded skip to show the safety rule. Finally, we run a full skip-aware intersection and report how many checks we saved. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by confirming the correct answer with the simplest trusted method. This snippet creates two tiny postings lists and computes the exact Boolean AND result. The lists are sorted document IDs for two terms, so the intersection represents documents containing both terms. Using set intersection is intentionally the easiest correctness anchor before we talk about cursor movement or skips. It does not model the work a search engine performs, but it gives us a trusted answer for later steps. The output shows the shared document IDs, which is the result every faster method must preserve. In practice, you run this once to ensure later optimizations do not change what documents are returned. And here, it gives us a clear baseline to compare against the scanning versions. The set-based answer is correct, but it hides the scanning cost we want to reduce. Next, we simulate the step-by-step scan that a simple engine would do, so we can instrument checks and see where time is wasted. This example walks through the same postings lists with a naive two-pointer and scan. The pane shows up in checks. Each loop compares the current IDs, then advances only one position unless there is a match. That is correct and linear, but it still touches entries like 3, 5, 13, and 21, even when a later jump would be safe. The variables I and j make the movement visible without adding ranking or scoring yet. The output shows both the exact hits and how many pairwise checks the naive scan needed. Watching those pointer moves is how we decide where a skip pointer could save work, because we can see repeated small advances that a single larger jump would avoid. Seeing repeated small advances motivates pre-computing jumps. Now, we build the skip structure and choose a spacing rule. Square root spacing is common because it balances pointer count and jump length. This code builds square root spaced skip pointers for tats using Python's standard math.isqrt. The skip map stores positions, not document IDs, because intersections need to move cursors cheaply inside the list. With 7 postings, step becomes 2, so each pointer jumps from one position to another 2 slots ahead when possible. More skip pointers shorten each jump but add more skip checks, while fewer pointers reduce overhead but miss more chances to jump. The output shows the actual dock ID to dock ID skip edges viewers can trace by eye. Inspecting that map helps you reason about whether a skip landing point might overshoot a potential match when compared to the other list. Before we commit all skips into the intersection loop, it helps to test a single guarded skip so the safety rule is obvious. This shows the exact condition that prevents missed matches. This snippet tests one guarded skip before putting skips into the full AND loop. A skip is only safe when the landing document ID is still less than or equal to the other list's current target. Here dogs is sitting at document 8, and the target 32 means landing on 21 cannot skip over a possible match. The skipped slice shows which ordinary postings would be bypassed by that one pointer. The output shows the skipped document and the Boolean guard, which is the safety rule that preserves exact results. Running that small check clarifies why we compare landing IDs rather than skip counts. With the guard rule clear, we can integrate both skip maps into the full intersection loop and count how many pairwise comparisons we avoid. This example runs a complete skip-aware Boolean and intersection and counts cursor comparisons. The loop still follows the same exact logic as the naive scan. Equal IDs are omitted and smaller IDs move forward. The new part is the pair of guarded branches that replace several next steps with cat skips or dog skips when the landing ID cannot pass a valid match. On this toy input, the result stays identical, while checks drops from the earlier naive count. The output shows the reduced check count and the unchanged final hit list, applied to a real inverted index. The same pattern holds. Build skip pointers for postings lists of moderately large terms. Pick spacing around the square root of the list length, and use the guarded check before every large move. The bookkeeping is minimal, and the saved comparisons add up when many queries touch long lists. It is a structure of pre-computed jumps that speeds up 2 list intersections. Use it when postings are long enough that cursor checks matter, and when memory for a few extra pointers is affordable. One thing to watch is skip density. Too many pointers add overhead, and too few miss opportunities to jump. Try tuning the skip spacing multiplier around the square root rule on a realistic corpus, for example the news or web crawl you work with, and measure cursor checks and latency to find the best trade-off for your load. If short practical IR helps, subscribe and watch the IR videos.